Okay, so just really quickly, before we get into 1.4, let's just take a quick stock of what we did in section 1.3. We introduced matrices as abstract objects, which don't necessarily need to arise from the context of studying linear systems of equations, although that's a great source of examples of matrices. That doesn't need to be where they come from. Then we defined the arithmetic operations. So we started with scalar multiplication. You can multiply any matrix by a scalar. Just simply multiply every one of its entries by that scalar. And that's really what, if you want to roughly phrase it, that's what scalar multiplication is. If you have two matrices that have the same dimensions, then you can add or subtract them just by adding or subtracting every corresponding entry. And if in addition, or if alternatively you have two matrices that satisfy a certain compatibility requirement, which we talked about when we defined matrix multiplication, then you can multiply them. And that the definition of matrix multiplication was significantly more involved than the other operations. But if you take all these operations, put them together into sort of a subject, you essentially get matrix arithmetic or matrix algebra, and that's what we're going to start studying in this section. So that's what 1.4 will begin with. So we're going to start by looking at some properties that we have. So properties of all the arithmetic operations that we have, and really this is going to tell us how the operations interact with each other. And the first one, well, actually let's start with some background first. We need to have some scalars. So we can call them anything we like. I'm going to call them alpha and beta, those two Greek letters. Those are going to be the symbols that I use for scalars or real numbers. And then I'm going to use capital A, B, and C for matrices. So I'll say and A, B, and C be matrices. Okay, so let's start with some properties. The first one says that if I add A plus B, where A is the factor on the left, and if I add the same two matrices but I put B as the factor on the left, then I get the same result. That's what this property is saying. So in order to convince you that this is not just some sort of empty statement, I want to draw your attention to a setting in which a property similar to this fails to hold. So for example, let's make a cautionary note over here. So in general, if I multiply two matrices A and B, that's not going to necessarily give me the same as if I multiplied them in the other order with B as the factor on the left. And let's look at an example of when this fails. Or let me phrase it differently. Let's look at an example for which these two products disagree, so they are different values. So I'm going to make up two matrices. The matrix A, I'm going to write it down as -1, 0, 2, and 3, so a 2 by 2 matrix. And I'm going to make B also be a 2 by 2 matrix. So those are the entries. So let's just calculate the products in both ways. So if I calculate A times B, well, then I have A on the left and B on the right. So I have a 2 by 2 and a 2 by 2. The product is defined, and the result will also be a 2 by 2. So just to make room, and now we can fill in the entries. So the entry right here, I'm going to have -1 times 1 plus 0 times 3. So that's going to be -1. The entry right here, I'll have -1 times 2 plus 0 times 0, which is going to be -2. Then down here, what will we have? We'll have 2 times 1 plus 3 times 3. That's 2 plus 9, so that's 11. And then for the last entry, I'll have 2 times 2 plus 3 times 0, which is just 4 plus 0. Okay, so that's what I get if I multiply them with A as the factor on the left. But what happens if I multiply them with B as the factor on the left? Well, I have the same two matrices, but the order is going to change, right? So this is what I will get. And again, it's a product of a 2 by 2 matrix and another 2 by 2 matrix, so the result is going to be well defined, and it will be a 2 by 2 matrix as well. So let's fill in the entries. So the entry right here, I'm going to have 1 times -1, 2 times 2, so that's -1 plus 4, so that'll be 3. The entry here, I'll have 1 times 0 plus 2 times 3. That's going to be 0 plus 6. Down here I'll have 3 times -1, 0 times 2, so that'll be -3 plus 0. And then for the last entry I'll have 3 times 0 and 0 times 3. Those are both zeros, so you add them together, you get 0. Okay, so really what's the point of this? Well, if I multiply with A on the left, I got this result, and if I multiply with B on the left, I get this result, and these are not equal. So that's the purpose of this example. So you can't, in general, expect the products, if you change the order of the factors, to be equal. And this is an example of that. So I'm just going to put a box around this because this is a separate note from our list of properties that we're writing down. But with that in mind now, come back up to here and you can see what I'm saying, right? This property, which is a property that is true, says that if you change the operation to addition, right, this was multiplication, but if I change to addition, it won't matter which order I add up the matrices in. So that's the first property. The second property is if let's say I had 3 matrices, A, B, and C, and I want to add them all up. So let's say I want A plus B plus C. Well, at this point, I'd have a choice to make. I'd have to decide, well, because addition is a binary operation, which means it takes two arguments. If you want to add up matrices, you have to add up 2 matrices, or at least at this stage, that's all we have. So I have to choose which of these matrices I'm going to add up first. So one option would be to add up B and C first. So first add B and C, and then take whatever the result is, and then add it to A. That's really what this means if I put brackets there. Another option, let me just write A plus B plus C again. Another option would be to add up the A and the B first instead. So first perform this addition, and then whatever the result is, now that's a single matrix I can add to C. So that's a choice you have to make at this point. Which one are you going to do? Now it turns out that it won't matter. They will give you the same result either way. So these two properties have names. The first one is called the commutativity of addition, and the second one is referred to as the associativity of addition. So these are two really important properties for addition. Now for multiplication, as we just commented over here, the order matters. So I'm not going to write AB equals BA because we just saw over here there's an example of when that fails. So, but we do have a property kind of like property 2 for multiplication, and it says the following. If I want to take the matrices B and C, multiply them together, then multiply the result by A with A on the left, that's going to turn out to be the exact same as if I first multiply A and B in this fashion and then multiply by C on the right. So this is referred to as the associativity of multiplication. So we don't have commutativity of multiplication because the order matters, right? We got 2 different values by changing the order of the factors, but we do have associativity, which is this property here. We also have a property which is called the distributive property, and this is the first property where you're going to be told how exactly multiplication and addition interact with each other. And here's what I mean by that. Let's say I have a matrix A and I want to multiply it by the sum of these 2 matrices B and C. Well, it turns out that if an alternative to this, one option is just to do this, perform this addition. Once you've figured out what B plus C is, then multiply it by A and work out the result. It turns out another option available to you is to first just multiply A and B directly, then multiply A and C directly, and add the results. And it turns out that's going to give you the same thing. So I'm going to put an equal sign here to say that those are those 2 expressions give you the same thing. And it actually works. There's some similar properties, yet they're still slightly different. If I have the multiplicative factor on the right of the summation, so let's say I had A and B and I want to add them, and then I multiply on the right by C, it turns out that this is just the same as AC plus BC. So that's the other way you can write the distributive property. That's how this tells you how multiplication will distribute into addition. Think of it, the A as being distributed into this sum, and each of those 2 terms gets multiplied by A. Same with this one. It's just getting distributed from the right instead of from the left. This is really, there's rules like this for the real number system, and that's really where FOIL comes from, if you remember how to FOIL out polynomials. There's similar properties involving subtraction. Just basically, if I take both of these properties and replace all the additions with subtractions, I'll get two new properties. So I'm just going to write those out. If I have a times b minus c, this turns out to give me the same as a times b minus a times c. And if I have the multiplication on the left, it also works. So I can distribute the c into the brackets like that, and I will get ac minus bc. Okay, so that's those are the distributive properties. There's another couple of properties that are kind of like these conditions, but they involve scalars. So what if I had two matrices, A and B, and I wanted to add them up and then multiply the result by a scalar alpha? Well, probably if you were to guess that the same sort of pattern will work, you'd be correct, right? This turns out to be the same as if I just multiplied the scalar A by alpha and then also multiplied multiplied the matrix A by the scalar alpha, then multiply the matrix B by the scalar alpha, and then add the two results. Because this is a matrix and this is a matrix. These are both the results of performing scalar multiplication. There's two scalar multiplications happening and then one matrix addition. Whereas over here, there's one matrix addition and then there's one scalar getting multiplied onto the result. So they are, it turns out though, this property tells you that they will give you the same result no matter what. And you can try it for a few matrices, just to write a couple matrices down and test it, and you'll see not only that it's true, but you start to see why it's true as well. We're going to look at an example after we finish this list. For number 9, it just says the same thing happens with subtraction. If I have a scalar alpha and I want to multiply it by the difference, a minus b, turns out another option, I could just multiply both a and b by the scalar alpha and then perform the subtraction afterwards. So that's the 9th property. And so a lot of these look similar, but yet they are still markedly different, like this one, for example. What if I add two scalars? Because remember, alpha and beta are the symbols for real numbers here. So these are scalars. So this is addition of real numbers happening inside these brackets. What happens if I multiply the resulting scalar onto the matrix A? Right? So there's addition of real numbers, and then whatever that number is gets multiplied onto A by scalar multiplication. You might guess that it would be okay to just go multiply the matrix A by each of the scalars separately and then add them together afterwards. And if you guessed that, you'd be correct. That will give you the same result. And then property 11 is similar yet slightly different. If you have the same thing but with subtraction, it also works. So if I had alpha minus beta times the matrix A, I can write this as alpha A minus beta A. That's really what those properties say. And the last two are as follows. So this one is very distinct from the ones that came first. Let's say I take the two scalars alpha and beta and I multiply them together instead of adding or subtracting like in the previous properties. So I'm going to multiply alpha and beta together. The result will give me a scalar, which I can then multiply onto the matrix A. So what is this going to be equal to? That's what this property is going to tell you. It turns out that another thing you could do is just forget about alpha for the moment. Just take the scalar beta and multiply that directly onto the matrix A. And then take the result of that scalar multiplication, and then which is going to be a matrix, right? This will be a matrix because you've got a matrix capital A multiplied by the scalar beta. So the result is a matrix, which you can multiply by another scalar, alpha. So turns out that these are the same. So what changes here? Here, the scalar multiplication is happening first. You have one scalar and you multiply it onto the matrix A. But over here, you have two scalar multiplications happening. The matrix A is being multiplied by the scalar beta. Once that's done, beta A is another matrix getting multiplied by another scalar alpha. So there's two scalar multiplications happening on the right, and there's going to be times when either one of those might be more advantageous than the other. Okay, so the last one now says the following. If I want to multiply the two matrices A and B, and I multiply the result by the scalar alpha, it turns out there's two other nice ways I might might want to use to compute this, that will also work. So another option is to just take alpha and multiply it onto the matrix A, and then the result will be a matrix which I can multiply by B. That will give me the same thing. Notice here the matrix multiplication happens first, then the result gets multiplied by the scalar alpha. This says I can multiply the factor on the left. I can multiply A directly by alpha, then this resulting matrix, multiply it by B, and I'll get the same thing. And it turns out there's actually, I can sneak it in here, I could also multiply A by the result that I would get from multiplying the matrix B by alpha. Okay, so that's all three of these things are equal. So those are the list of properties that I wanted to start this section with, as well as a comment on one property that you absolutely don't have. So please do not make the mistake of thinking that matrix multiplication is not affected by the order in which you write down the factors. It absolutely is. And this example gives you right away a case of this. But for the rest of these properties, notice I didn't make any mention of the dimensions of A, B, and C, just because it gets a bit tedious to write down all the particular requirements, because all these different properties would have different requirements. Like for example, for the first one to even make sense, you'd need A and B to both have the same dimensions to be able to add them together. But then for property 3 to make sense, you wouldn't need them to have the same dimensions. You would need B to have the same number of columns as C has rows, and so on. And you need A to have the same number of columns as B has rows. That's the compatibility condition for multiplication. And if I were to go through each one of these properties and write out carefully what the conditions would be for them to make sense, it would get a bit silly, to be honest. So what I'm going to do instead is just do the following. So I'm going to draw an arrow and say it is understood that these properties will hold true whenever A and B and C, these matrices up here, have appropriate dimensions. So whenever A, B, and C have appropriate dimensions, so that all operations are defined. That's really what we mean. And if A, B, or C has a particular set of dimensions so that either the left or the right-hand side of any of these equations is not defined, well then the other side of the equation will also not be defined. So really, when these things make sense, these properties tell you they're going to be equal. That's how you should interpret that. So I said we're going to do an example, and I'm going to pick one of these properties to do an example of. There's more in the exercises for you to check on your own, but I'm going to come up with an example to show that this statement is true, property 3, and show you exactly what it means for this statement to be true in the case of particular matrices. So here are the matrices we're going to use. So, and the example is going to be to check that these matrices, so here are the matrices. A is going to be a 3 by 2 matrix. And then B is going to be a 2 by 2 matrix. It's 4, 3, 2, and 1. And then C is going to be another 2 by 2 matrix, given as follows. So check that those three matrices satisfy property 3. That's what we're going to do. So in other words, check that this equation up here, property 3, is satisfied when A, B, and C are given by these matrices. So how are we going to do this? So let's perform the check. Okay, let's start by working out the left-hand side. So let's work out what A times the product of B and C would be, right? So I'm just writing down the left-hand side of the equation listed in property 3, and we're going to carefully work it out. And then we're going to do the same thing for the right-hand side. So the brackets say that we're going to multiply B and C first. So I'm going to just zip over here to the other area of my page, and I'm going to just do that calculation separately. Let's multiply B and C. So we're going to multiply the matrix B by the matrix C. So it's a 2 by 2 multiplied by another 2 by 2. The result is going to be defined and will equal 2 by 2. So let's work out the entries. So 4 times 1 and 3 times 2, that's 4 plus 6, which is 10. 4 times 0 and 3 times 3, that's 0 plus 9. Then for the second row, we'll have 2 times 1, 1 times 2. It's going to be 2 plus 2. And then 2 times 0, 1 times 3, that'll be 0 plus 3. So that's the product of B and C. You'll get this matrix. So when I go to work out A times the result, really what this means is I have the matrix A, and I'm going to multiply it by the product of B and C, which is over here. So 10, 9, 4, and 3. So now we've got another product, right? We've got a 3 by 2 and a 2 by 2. So the result will be defined, and it will have dimensions of 3 by 2 as well. So let's work out the entries. So 1 times 10, 2 times 4, that's going to be 10 plus 8. 1 times 9 and 2 plus 6, that's going to be 9 plus 6, which is 15. 3 times 10 and 4 times 4, that's going to be 30 plus 16. And then what will be here, we'll have 3 times 9 and 4 times 3, that's going to be 27 plus 12, which is 39. And then for our last row, 0 times 10, 1 times 4, that's going to be 0 plus 4. And then 0 times 9, 1 plus 3, that'll be 0 plus 3. So that's what you get if you work out the left-hand side of this equation in property 3. So now let's work out the right-hand side and see if we get the same thing. By this property, we're expecting to get the same thing, but let's see if we actually do. So to work it out carefully, we're going to multiply A and B first, and then multiply the result by C. So this is the right-hand side of the equation in property 3. So now we have to multiply A and B first. So I'll just copy the same trick I did over here. I'm just going to move over to the side of the page a bit and multiply A and B carefully. So A is 1, 2, 3, 4, 0, 1. That's the A, and then B is 4, 3, 2, 1. So again, we have a 3 by 2 multiplied by a 2 by 2. The result will be defined, and it will be a 3 by 2 as well. So let's work out the entries. We've got 1 times 4, 2 times 2, that's 4 plus 4, which is 8. Then we'll have 1 times 3, 2 times 1, that's going to be 3 plus 2, which is 5. 3 times 4, 4 times 2, that's going to be 12 plus 8, which is 20. And then over here, what do we have? 3 times 3 and 4 times 1, that's going to be 9 plus 4, which is 13. And then our last row, 0 times 4, 1 times 2, that's going to be 0 plus 2. 0 times 3, 1 times 1, that's going to be 0 plus 1. So that's our product AB. So now we can work this out because this will be what we put in for AB. So we're going to have 8, 5, 20, 13, 2, and 1. So that's our product of multiplying A and B, which we just did over here. And then now C, we're going to put immediately to the right. So we're going to put a copy of C here. So 1, 0, 2, 3. So we've got a 3 by 2 times a 2 by 2. The result will make sense. They satisfy the dimension requirement, and the result will have the dimensions 3 by 2 as well. You can draw the dimension diagram to check that if you like. So let's work out the entries. 8 times 1, 5 times 2, that's going to be 8 plus 10, which is 18. So far so good. That matches up with the 18 up here. We're expecting all of these to be the same, but let's check them. Here if we go 8 times 0, 5 times 3, that's going to be 0 plus 15, which is 15. For the second row, 2 times 1 and 13 times 2, that's what? That's 20 plus 26, which is 46. Our third entry, the second entry in the second column, we'll have 20 times 0 and 13 times 3, so that's going to be 0 plus whatever 3 times 13 is. So 3 times 10 is 30, and 3 times 3 is 9, so you have 39 here. And then our third row, we've got 2 times 1, 1 times 2, that's going to be 2 plus 2, which is 4. And then lastly, 2 times 0, 1 times 3, that's 0 plus 3. So we got it, right? These two matrices are the same. So therefore, at least in this case, it follows that if I multiply B and C first, then multiply on the left by A, that's the same. I get the same result as if I first multiplied A and B and then multiplied the result by C. Okay? At least in this case, this shows that that actually works, at least for these three matrices. But this property, along with all these other properties, these are telling you what is going to be true in general, no matter what you choose your matrices A, B, and C to be, as long as they have the appropriate dimensions, remember, so that all these operations required to write down these properties are actually defined. Okay, so that concludes that example.